Good afternoon. Today I'm going to talk about Gaia, Geo-Distributed Machine Learning Approaching LAN Speeds. This is a joint work with my collaborators in Carnegie Mellon University and ETH Zurich. So I'll begin the talk with an overview of the problem and the goal of our work. As we all know, machine learning is very useful in many applications with large-scale data. For example, you can do image classification or video analytics or user preference prediction. However, a lot of large-scale data is actually geo-distributed because there are many data centers deployed all over the world, and so actually a lot of data is generated at very high speed across the world. So to run machine learning across these geo-distributed data, the most straightforward approach is to centralize this data into one data center before you run the machine learning application. However, as many prior work has argued, centralizing data is actually not feasible because moving data across a wide area network will cause a lot of overhead and it can be extremely slow. And also, it will subject to data sovereignty law constraints. For example, some user data may not be able to move out of EU because there are some EU law constraints. So the alternative approach is we deploy a geo-distributed machine learning system, which means we make the data stay with their own data center, but we deploy machine learning system across multiple data centers. However, this approach is also very challenging because no machine learning system is actually designed to run across multiple data centers. And based on a study, such deployment compared to running everything within a single data center can cause up to 53 times slowdown. So to solve this problem, our goal of this work is we would like to develop a geo-distributed machine learning system that can minimize communication over wide area networks, and we still retain the accuracy and correctness of machine learning algorithms. And also, we want to do that without requiring any change to the machine learning algorithms themselves. So it sounds like a hard problem, but so the question is, can we solve this? So obviously, the answer is yes. So our result will show that our system will improve the system performance by 1.8 to 53.5 times speed up compared to state-of-the-art machine learning system deployed on wide area networks. So now I'm going to take a step back to give some background and motivation of this work. So I'll give a background of the parameter server architecture. This is a state-of-the-art machine learning system architecture that has been adopted in many distributed machine learning systems. So from very high level, a machine learning application is one to use the training data to generate the best machine learning model. So this process of training, with the help of parameter server architecture, so the parameter server will first split the data into multiple data partitions and have many worker machines to handle each data partition. And then it will have multiple parameter servers, and they collectively maintain the machine learning model. So at each iteration of training, the worker machine will generate the update to the machine learning model, and then it will read back to the up-to-date parameter values from the parameter server. And this synchronization process of each iteration is very, very important for the accuracy and correctness of machine learning algorithms. So to deploy a parameter server architecture into multiple data centers, the most straightforward approach is we have the worker machines within each data center to handle their training data, but we deploy the parameter server across multiple data centers. However, this approach, although it's very simple, it will cause all the communication from worker machines to remote data center going across the wide area networks, and it can seriously slow down the system. So to understand how limited the wide area network bandwidth is, we study the wide area network bandwidth across 11 Amazon EC2 regions. And based on our study, on average, the wide area network bandwidth is 15 times smaller compared to local area network bandwidth. And it can be up to 60 times smaller. And another problem of using wide area network is there are extra costs associated with that. For example, in Amazon EC2, if you communicate with full wide area network bandwidth, the extra communication cost can be up to 38 times of the machine cost if you use a cheap machine. So now let's see how wire network affect the performance of machine learning system. So we study two state-of-the-art machine learning systems, ITER-Store and Boson, and both run the same machine learning application, metric factorization. So in this figure, we show the y-axis is the normalized execution time until algorithm convergence. So all the results are normalized to ITER-Store running on LAN, which is all the data is preloaded at single data center, and then we run everything within single data center. And we test 3 deployments. The first deployment is we deploy the system across 11 Amazon EC2 regions. And the second deployment is the deployment between Virginia and California, so the test of the same continent deployment. And the third deployment is deployment between Singapore and Sao Paulo. This is the worst wide area network bandwidth pair that we can find among these 11 Amazon EC2 regions. So as we can see, all these 3 deployments will cause serious slowdown to ITER-Store. It's between 3.5 times to 23.8 times slowdown. It's also very similar to Boson. It's between 4.4 to 24.2 times slowdown. So we can see that if we simply run a machine learning system across multiple data centers, it can cause serious slowdown to machine learning applications. So now, to solve this problem, we propose our system. We call our system Gaia. And here I'm going to introduce it. So as we can see, the major problem of running the parameter server across multiple data centers is the communication between worker machine to remote parameter server that go through the wide area network. So our key idea of Gaia is we decouple our synchronization model within the data center from the synchronization model between multiple data centers. So here is how it works. So within a single data center, we still have multiple worker machines that handle the training data. And we, again, have multiple parameter servers to handle the model. Now, the major difference is within each data center, we will have a full, approximately correct model copy. So because it's a full copy, so the local worker machine only need to talk to local parameter servers to do synchronization and make progress. They don't have to talk to other parameter servers. And in the other data center, they will have another model copy. It's also approximately correct. So we say it's approximately correct because we allow some acceptable difference between each model copy. And we will run another synchronization model that we call remote sync here, is to make sure that they are still within the acceptable difference. So as a result, we only need to communicate the updates that is significant, that actually will change the model that for us to maintain the approximately correctness over wide area network. So to see how this architecture can help us, we study the update significance from 3 machine learning applications: metric factorization, topic modeling, and image classification. In this figure, the y-axis is the percentage of insignificant update, and the x-axis here is the threshold of significance threshold. For example, 1% means that if an update changes the parameter value by more than 1%, then we say it's significant. Otherwise, it's insignificant. So as we see, even we use a relatively small threshold, such as 1%, we can see that more than 95% of the updates are actually insignificant, which means the vast majority of the updates are actually insignificant, and our Gaia architecture will be able to eliminate most of them. So now I'm going to introduce a new machine learning synchronization model that we call Approximate Synchronous Parallel, that we use as a remote synchronization between multiple data centers. So our Approximate Synchronous Parallel model has 3 components. Because of limit of time, I'm going to introduce the first 2 components, and the third component is a detail is in the paper. So the first component is the significance filter. Pretty much is the mechanism that we filter out the significant updates from all the other updates. So the way the significant filter works is whenever a worker machine generates an update to the parameter server, let's say delta 1, this parameter server will maintain the value of parameter x and also an aggregated update of parameter x. For example, if the initial value of the aggregate update is 0, then this delta 1 will be aggregated into this aggregate update field. So now the aggregate update becomes delta 1. And this process will keep happening, and all these updates will be aggregated into this aggregated update field until the end of iteration. Now, the parameter server will send the value of parameter x and the aggregated update of x into the significance function. And this significance function will generate the significance of the aggregated update. And then it will use the significance to compare against the significance threshold. If it's larger than the threshold, then it will share the aggregated update to other data centers and reset the aggregated update. Otherwise, it will just keep the aggregated update within this data center. The significance function can be very simple, such as the ratio between the aggregated update to the parameter value itself. And the significance threshold can be also very simple, such as 1%. But we will apply a function to make the threshold smaller and smaller so that eventually all the data centers can see all the updates. Now, we have our significant updates. We'll talk about the second mechanism in the approximate synchronous parallel that's called ASP Selective Barrier. So we need this mechanism because even though we already only send the significant updates, it can still overwhelm the limited wide area network bandwidth so that all these updates can arrive too late. So to solve this problem, whenever we have significant updates, we will first send a selective barrier to another data center so that the other data center will block those parameters from being read by their local worker until the significant update arrives to resolve those barriers. So as we can see, the benefit of this design is that only the worker machines that depend on these parameters will be blocked, while the other workers can keep making progress. So now I've introduced the key components of our Gaia system. I'm going to put everything together to talk about how we implement it. So we implement our Gaia system based on the parameter server system. So we again have the worker machines to handle the training data, and all the change happen within the parameter server. So we will have, within the parameter server, we will have local server to handle the local synchronization with local workers, and we will have our parameter store to store the parameter value and the aggregated update of each parameters. And also we will have the significance filter as we just introduced. And then we will have the mirror server and mirror client to handle the remote synchronization with the other Gaia parameter server in other data center. And between the significance filter and the mirror client, we have control queue and data queue to handle the messaging. So the way it works is, again, when we have an update from worker machine to parameter server, it will first send to the local server, and the local server will send it to the parameter store, and as we said, it will eventually become the aggregated update. At the end of each iteration, this aggregated update will be sent to the significance filter to check if it's significant or not. If it is significant, it will first generate a selective barrier to the control queue, and then the aggregate update go to the data queue. And we always prioritize the message from control queue over data queue, so these control messages will be always seen first. And as we can see, all these changes happen within the parameter server. So we don't change the worker machine. So of course, we don't change the machine learning algorithms or the machine learning programs. And another implementation problem that we find is that even we only send a significant update to other data center, we need to broadcast them to all the other data centers, which means that when we have a lot of numbers of parameter servers, the communication overhead will be proportional to the number of data centers, which will limit the scalability of our Gaia system. So to mitigate this problem, we adopt the idea of overlay network and hubs. So the idea is that we will make the geographically closed data centers to form a data center group, and we will assign hubs within each data center group. So whenever we have significant update, we only send this significant update to the hub, and then the hub will broadcast to the other hubs. So with this mechanism, we can save the communication on wide area network because we can aggregate the hub at the sending hub, and also we can aggregate those updates at receiving hubs to save the overall traffic. So now let's take a look at how our system performs in our evaluation. We evaluate our system with 3 machine learning applications: metric factorization, topic modeling, and image classification. And our Harlap platform consists of 22 machines that we emulate the wide area network bandwidth in Amazon EC2. And we also validate our platform performance with a real EC2 deployment. Our baseline is Ether Store and GPS deployed on wide area network. Both are state-of-the-art machine learning systems. And also, our performance metrics is the execution time and the cost of running the machine learning applications. We first look at how our system performs when we deploy across 11 EC2 data centers. The y-axis here, again, is a normalized execution time. So as we can see, across the 3 machine learning applications, our Gaia system is significantly outperformed baseline. Overall, it's 3.7 to 6.0 times speed up over baseline. And also, it's also very close to the performance of LAN, which is we preload the data into a data center and then run everything within a single data center. So in this case, we can see that Gaia is only at most 1.4 times of the speed of LAN. We also evaluate our system with different wide area network bandwidth deployment. The first deployment we test, again, is the Virginia-California deployment to represent a single continent wide area network bandwidth. As we can see, in this relatively high bandwidth deployment, the performance of Gaia is pretty much the same as the performance of LAN. And the second deployment we test, again, is the worst case of Amazon EC2 pairs, Singapore and Sao Paulo. In this very challenging deployment, we can see that Gaia can still successfully approach the speed of LAN and achieve a significant speed up over baseline. In the best case image classification, we are able to achieve 53.5 speed up over baseline. Overall, Gaia achieves 3.7 to 53.5 speed up over baseline, and is only at most 1.23 times of the LAN speed. Lastly, let's take a look at the cost of running our system and baseline over wide area network. In this figure, we show the normalized cost of running the machine learning application. In this figure, this is metric factorization. And we segment the cost into the communication cost on wide area network, and the machine cost, the waiting on network, and the machine cost that do real computation. As we can see, across all these deployments, Gaia is significantly cheaper than baseline, mostly because we successfully minimize the cost of communication over wide area network, and also we reduce the cost of waiting on network. It's pretty much similar for the other 2 applications as well. Overall, we can see that Gaia is 2.6 to 59 times cheaper than baseline. There are a lot more in the paper. We actually offer a theoretical proof of convergence with our new Approximate synchronous parallel model. And also, we have the results with enable our Approximate synchronous parallel model without the synchronization model to show that why this is so critical to have a synchronization model. And also, we have our performance with our system and compare with the approach that you can somehow centralize all this data into one data center. So to summarize, the key takeaway of this talk is that the problem we will try to tackle is how do we perform machine learning on geo-distributed data. This is a challenging problem because centralizing data is infeasible, but simply running geo-distributed machine learning can be very slow. Our Gaia approach consists of 2 key components. The first component is we decouple the synchronization model within the data center from the synchronization model between different data centers, so we can eliminate the insignificant update across multiple data centers. The second component is we introduce a new synchronization model that we call Approximate synchronous parallel, that we can retain the correctness and accuracy of machine learning systems. Our result shows we can achieve 1.8 to 53.5 times speed up over state-of-the-art machine learning systems over wide area networks, and it's only at most 1.4 times of the LAN speed, and also we can achieve that without requiring changes to the algorithms themselves. With that, thank you. I'll be glad to take questions.
Li Chen from HJST. Really impressive work. I really like it.
Thank you.
I have a question comparing this to the machine learning literature. For example, how do you compare ASP with SSP, basically stale synchronous parallel? In my view, you are controlling the versions between the parameter servers, but SSP is controlling the divergence between the workers. Can they coexist, or what's your opinion on that?
Okay, it's a very good question. So the major difference of ASP and SSP fundamentally is that we only send the significant updates, but SSP still have to send the updates to all the other data centers. The only difference is you allow that the machine learning worker to make progress even without some updates. But all the updates still have to be communicated. So in fact, we have some results in backup slides. Let me show it. That we also evaluate the SSP compared to so in this figure you can see that there's a results with BSP and results with SSP, right? So you can see that even with SSP, the performance of baseline and Gaia is there's still a gap there, and also the Gaia performance is much closer to LAN compared to SSP. And for the other, we also have other results with more challenging setting. For example, for the results with the most challenging case that SS went between Singapore and Sao Paulo, you can see that using SSP really doesn't actually improve the performance much in this setting. But Gaia is successfully closed the gap between LAN and baseline.
Okay, thank you.
Thank you.
One more. Yeah. Stuart Wagner, DARPA. Certainly reducing the wide area network load is extremely important, so this is great. But I'm wondering if you can take it a step further. So the achievable good put that you can get across any 2 points on the edges of a WAN can vary wildly over time, and in fact can get very, very small for extended periods of time. So I'm wondering, is there a means for you to detect that and then say to vary your update threshold in a way that takes into account the fact that, gee, I thought I had this much, but in fact I only have that much, without significantly impairing the ML algorithm?
Right. So there are some detail in the paper we talk about it. So in fact, we have actually two thresholds in our system. One threshold is that we have to at least hit that threshold so that we can guarantee the correctness of algorithm. But there is another threshold that we can tune based on the underlying wire network bandwidth. So if we have more bandwidth, we can send more updates. But if the bandwidth is smaller than the threshold that we still require to make sure our correctness, we still have to send those updates. But that will slow down the system in that extreme case.
Right, okay. Maybe we can get together afterwards and talk about it more.
Thank you.
All right, let's thank the speaker. One more time.